So the topic of this presentation and my research is tiling systems, and my field is mathematics and theoretical computer science. But this presentation will not contain any equations or formulas to keep it understandable to all the fields that are present. So the basic object in tiling systems theory is a tiling, and it means a covering of the two-dimensional plane, they're like an infinite flat surface with tiles, and tiles are geometric shapes basically, and the covering must be exact, the tiles don't overlap, and they cover every point of this surface. You can think of your bathroom wall with some ceramic tiles. Here is an example of a tiling. You have geometric shapes. These are rectangles, and the red ones are triangles, and they cover everything, and it continues like this in every direction. So this tiling is periodic, meaning that it repeats exactly the same everywhere. So if you shift it by, let's say, 3 centimeters to the left, so that every rectangle goes to the place of the next one, you will have the same tiling. It doesn't change if you shift it a little. Okay, so this is a tiling. It's not a very interesting tiling because it's everywhere the same. Here is a bit more interesting tiling. So those of you who live here in Helsinki may recognize this tiling. It's in Keskuskatu, and it's the so-called Penrose tiling. The green tiles are called kites, the red tiles are called darts. And this tiling has the interesting property that while it locally looks very similar at different places, it doesn't ever repeat exactly the same. So here you can see like a red star on the left, and here you can see a red star on the right. But their surroundings are different if you go a couple of steps to the right. So the other one is surrounded by a red circle, and the left one is not. And the property is that if you look at any two positions here, at some point you will see a difference when you look far enough from these points. So we say that these tiles are aperiodic. This tiling is not periodic, doesn't repeat exactly the same. Okay. So my research is a bit closer to the computer science. So I want to be able to represent my tiles in the computer, and I want them to be as simple as possible. So I use a slightly different model called Wang tiles, which are named after the logician Wang. So Wang tile is always shaped like a square, but it might have some markings on it. So here's a tile which has a black circle, and on the borders it has a dark gray bar and a light gray bar. And when I put two of these tiles next to each other, I enforce that the markings must be the same on the border that they share. So this tile and the next tile, I can put them together because they both have the dark gray tile on this border. But I cannot put it next to the middle tile because the middle tile on the left, it has a white border, but this tile on the right, it has this dark gray thing, so they don't match. And if we want to stay in the geometric shapes, idea, we can always model our Wang tiles as these kinds of squares with bumps and holes on the sides that kind of fit together like locks and keys. So this dark gray is this large bump and the white is the smaller bump, so you cannot fit the small bump in a large hole. Okay, and now you can try to build a tiling out of these Wang tiles. Here's one. We have the black dots there, and we have these gray markings on the edges, and every time we have a gray marking, we also have to have a gray marking on the other side of the same shade. Okay, and now we see that these gray markings, they enforce some constraints on these black dots. And the constraint is that you cannot put two black dots next to each other, because a black dot always has a white thing, a white border on top and on the left. But on the bottom it has a gray thing, and on the right it has a gray thing, so they never match. So if we remove those gray markings, then we always have this sort of a configuration of the black dots where you don't have any two neighboring tiles with the dots. Okay. But we can also do this from the other direction. So we start with some constraints on these black dots, and then we try to find markings that enforce exactly these constraints. And this is a part of what my research is about. I'm taking some sort of abstract or complicated constraints over these black dots, and I ask, can I find markings that enforce these constraints? Here's some terminology. So a Wang tile, a set of Wang tiles always gives me a system of finite type, which means that all the constraints are local. So I'm only enforcing something about tiles that are next to each other. I have no long-range constraints other than what comes from these local interactions. And if I erase these markings, I have something called a suffix system. So suffix is a word that comes from Hebrew and also means finite. And you can see that's the system having hidden local constraints. So behind the scenes, there are some local interactions that completely force the structure of the system. And then the question is, we are given some constraints. Do they give us a suffix system? Can I find a set of Wang tiles that implements them? Okay. Here's a slightly more complicated example. So I am asking that if I look at the black dots in my tiling, they form some groups that are connected. You can think of them like islands in the sea of white tiles. Okay. And I'm asking that every island must have an even number of dots, 2 or 4 or 6 or 8 or 10 and so on. And this constraint, it turns out, can be enforced with a pretty simple system of Wang tiles. So I just add some decorations to these black tiles, and the white tiles can all be white. So here's an example of the even groups system. I have these islands here. Here's an island of 6 dots. Here's an island of 4 dots, and so on. These are the islands. You can check that they have an even number of black dots. And here are the hidden constraints behind these constraints. So the hidden local rules. So it can be checked. I won't explain now how it can be checked, but it can be checked that these rules give exactly the system of even groups of dots. So every black dot has either 1 or 3 gray markings, and the gray markings connect 2 dots. Right. So we can do even size groups. Can we do odd size groups? It turns out that we can do them. And for this, the construction is much more complicated. There is an article in the making about this, which has not yet been published, but I know the people who are working on it, and they have explained it to me, and I believe them. But this was for some time an open problem whether this could be done. I'm not showing the tiles here because there are many of them. But here's an example of the odd groups system, and here are the groups of odd size. It's a group of 7 dots and 5 dots and a couple of 1-dot groups. Okay, but then we also have some systems which cannot be implemented with these hidden local constraints of Wang tiles. So the so-called mirror system is a standard example. So in the mirror system, you have a vertical line consisting of red dots, and then you also have black dots. And the left-hand side and the right-hand side of the red line must be mirror images of each other. And this is not possible to realize with Wang tiles. Here's an example of a configuration of the mirror system. And the intuition behind why it cannot be realized with Wang tiles is that for every pattern on here on the left, you must have the exact same pattern on the right side in the same position. So you must know exactly what the contents of this pattern are, but you have only so much space on the border of the pattern to kind of get the information out. You have too much information inside the pattern and too little space on the border. And this can be made precise, so we can actually mathematically prove that this system cannot be realized with local constraints. And this is one of the sort of large open problems in the theory of Wang tiles. So what is the class of systems that can be implemented with hidden local rules? What is the class of suffix systems? There are some classes of systems which we know that are sophic, which can be pretty complex. There are some classes which we know are not sophic, but there is a pretty large gap in between systems that we don't know if they are sophic or not. Okay. Now another branch of research is the study of the Wang tiling systems themselves. So we can ask about properties of a given system of Wang tiles. I'm given the set of Wang tiles. It's a finite set. I can encode it, give it to a computer, and ask the computer to tell me something about this set of tilings that they generate. So I can ask, okay, does there exist even one infinite tiling? I can ask, does there exist a tiling that repeats itself, which is periodic, like the first example with the squares and triangles. I can ask about the entropy. The entropy is a single number associated to a tiling system. It sort of approximates how many finite patterns of some size there are. But instead of having different number for each size, we have one number that sort of compresses this information into a single well-behaved thing. But it turns out all these questions are unsolvable. There is no computer program that can ask for a set of tiles and tell me whether a tiling exists. And when this was realized, people were sort of disappointed because nothing could be said at all about tiling systems. Everything is undecidable if you want to be formal. So undecidable means that there is no computer program that can check a property. And this problem was called the swamp of undecidability by some researchers, a little tongue-in-cheek maybe. Okay, but why study these properties if nothing can be said in general? So there are some special cases which are more or less solvable. If I can guarantee that my tile set is in some sense well behaved, then my computer program may be able to say something about it. And especially with these well-behaved tilings, there are connections to statistical physics. This is where the notion of entropy comes from. So I can see my set of tiles as a lattice of some particles, or maybe some atoms of gas in a container, and I can ask something about the number of different allowed configurations, or I can generate a tiling at random, and then it somehow resembles a random configuration of this physical system. I can ask how many ways of randomly choosing a tiling there are, and so on. We can also use these unsolvability results to our advantage. So if we know that tilings are very, very difficult to analyze, and we know that in some other system we have some things that look like tilings, then we know that this other system is also very difficult to analyze. And this has been used for showing that DNA computing is very difficult, or analyzing what DNA computing does is very difficult. So DNA computing means is that, so you take strands of DNA, they bind to each other if you put them in one container and stir it up, and you can make them form these different shapes. And it turns out that you can make them form shapes that look like Wang tiles. And then these Wang tiles form DNA tilings, and because you cannot analyze tilings, you cannot in general analyze what the DNA computer does. And fourth, in this abstract theory of tiling systems, we can also use this unsolvability in some sense. We can quantify it. So it turns out that there are different degrees of unsolvability. So some unsolvable things are more unsolvable than others. It means that if I have a magic computer that can compute infinitely many steps in 1 second, maybe I can compute some things about tilings, but not others. And then we can have a nice hypothetical hierarchy of problems in tilings. But also we can use this to characterize properties of tilings. So I told you that entropy of a tiling is not computable. And also, not all numbers can appear as entropies of tiling systems. So there are some numbers which are sort of very, very complex. You cannot write a computer program that lists the digits of this number. And if it's complicated enough, then it also cannot be the entropy of a tiling system. And this has led to a result of characterizing the possible entropies of tiling systems, which is very abstract and maybe not useful for many things, but it was sort of a groundbreaking result in this theory when it was first published around 2008. So if your number is not too uncomputable, then you can construct a tiling system which has this number as its entropy. So we know exactly which numbers appear as entropies of tiling systems. So you cannot get the entropy of a tiling system, but you know when you can get a tiling system from an entropy. And after this and some similar results, there was a sort of an explosion of new research activity in this computational tiling theory. And many other things are known now, and this has led to many interesting but very abstract results. So maybe this is not related to any concrete applications, but I find it very nice and interesting. Okay, this was my last slide.